Welcome back to Buffers and Titration. We are now going to titrate a weak acid with a strong base. Are you ready to get started? Let's go. So a titration of a weak acid with a strong base is very similar to a strong titration, except that with a weak acid, strong base, you'll end up with a basic salt instead of a neutral salt at your equivalence point. And then at the end point you'll end up with a base, just like you do with a strong titration. So the math itself will be very similar, except that since you've got a weak acid, you're going to be dealing with the Ka formula. Let's just look at it. So if we have 50 milliliters of a 0.2 m HAC, or acetic acid solution, titrated with 0.1 m NaOH, that means in our Erlenmeyer flask we have HAC, and in our burette we have NaOH, and so we're going to pour the NaOH drop by drop into the HAC until the endpoint is reached. So as far as the calculations, how many milliliters of NaOH will be required to reach the equivalence point? This is the same as it was with a strong titration. MAVA equals MBVB. The number of milliliters required to reach the equivalence point is the same whether it's a strong acid or a weak acid. So for the acid, that is 0.2 molar times 50 milliliters. And for the base, that is 0.1 molar, and who knows milliliters. So 0.2 times 50 divided by 0.1, we end up with 100 milliliters of NaOH needed. To reach the equivalence point. That'll give me the same number of moles of OH minus as I have moles of H plus. So then, how many moles of H plus do I have? How many moles of HAC are present initially? Well, I have a 0.2 m HAC solution, and I've got 50 milliliters of that. Notice I'm using liters here since I want the number of moles. So that ends up with 0.01 moles acetic acid initially. That's just molarity as moles over liters. Alright, let's get down to the nitty-gritty. What's the initial pH of the HAC, and how is this calculated? So look back again at your formula. HAC plus water is going to make H3O plus AC minus. Notice that my formula does not have NaOH in it. First of all, because I haven't added any NaOH to my solution, but even if I had, I hadn't added enough to get to the equivalence point. So I have a 0.20 molar HAC solution initially, and then a 0 here and a 0 there. We're going to minus x plus x plus x. Hopefully this K equation is looking familiar to you. Ka is equal to H3O plus times AC minus over HAC. And so that is 1.8 times 10 to the negative 5 is equal to x squared over 0.20. So multiply both sides by 0.2, then take the square root. X is equal to 1.9 times 10 to the negative 3. And that is molarity, the concentration of the H3O plus. So then the pH is just the negative log of this H3O plus. And since that's a negative 3, this should be 2 point something, 2.72. So how is this calculated? Well, since no base has been added, the pH is determined only by the HAC. So we're going to use the Ka equation for HAC. Since there's been no base at all, I don't have to worry about the NaOH at all. But what happens when I do add base? Let's find the pH after the addition of 20 milliliters of 0.1 molar NaOH. So 20 milliliters of 0.1 molar NaOH, that ends up being 0.002 moles of OH minus. And add it. And that's how much OH minus I'm going to add to my solution. Now for my equation, it'll be the same equation as we had before. HAC plus water makes H3O plus AC minus. And my initial HAC moles will be the same as it was before. That is 0.01 moles of HAC. Notice that I'm using moles here and not molarity, because now that I have 20 milliliters added, a new volume, my molarity will change. So I'm going to deal with moles initially, and then I'll come back and deal with molarity. So I'm adding 0.02 moles of a base. And when you add to a base, it adds to the base and subtracts from the acid. So I have 0.002 moles of the OH minus subtracting from the HAC, which leaves me 0.008 moles of HAC left over in excess. Now initially, at the beginning, I had 0 AC minus, but when I added a base, it adds to the base 0.002 moles from my initial 0, leaves me with 0.002 moles of AC minus produced. So what's happening in this reaction is that the OH minus is reacting with this HAC and taking a hydrogen from that HAC and causing AC minus to be produced and some extra water. Well, let me look at my total volume. The 20 milliliters plus the 50 milliliters I had originally is 70 milliliters. So I'm going to divide them both by 70 milliliters because I can't actually do any pH calculations without molarity. So now that I've figured out what the moles are going to be, I'm going to convert them to molarity. Dividing by that 0.07, because that's my new total volume, I end up with 0.11 molar HAC and 0.029 molar AC minus. At this point, the reaction comes to equilibrium. Minus X plus X plus X. Remember, my H3O plus started at 0, so 0 plus X is X. I'm going to use my Ka equation that I did before. That is H3O plus times AC minus over HAC. Remember that Ka is 1.8 times 10 to the negative 5. This time, instead of having x squared over our concentration, I'll have 0.029x over our concentration, 0.11. So multiply both sides by 0.11, divide by 0.029, I end up with x is equal to 6.8 times 10 to the negative 5 molar, and that is my H3O plus concentration. So if I want my pH, that'll be the negative log of H3O plus, which is 4.17 for my pH of the solution at this point. So what is happening in this reaction? Well, all of my added OH minus reacted with some of my HAC. Not all of my HAC, I'm not quite to the equivalence point yet, but some of my HAC to produce AC minus. So at this point I kind of have a buffer because I've added some OH minus to produce AC minus, so I have both the weak acid and its conjugate base. So if you want to think about it as a buffer, but initially it's not a buffer, and at the end point it won't be a buffer, but here in the middle range it will be a buffer. So how is this calculated? Well, when you add a base, it adds to the base. But what's important here is it adds to the base moles, not adds to the base molarity. So we'll take the moles of base added to the moles and subtract from the acid. But make sure it is the moles. You're subtracting the moles of base from the moles of acid, and then divide by total volume to get molarity. Once you've added the moles to the moles and subtracted the moles from the moles, then you're going to divide by total volume to get your molarity, and then at that point, use the Ka expression. To find x. So at that point you can minus x plus x and get x is equal to H3O plus and then move along as if it's a regular problem. Alright, let's look at the pH at the midpoint of the titration. That is halfway there. Remember our initial problem we were trying to figure out how many milliliters were required to get the equivalence point was 100. So now we're at 50. We're halfway to where we're supposed to end up being. So we have an equation. Every single time I write an equation will tell you what's going on and what's in the beaker and what's not in the beaker. So write an equation. And now we're going to set it up like we did before with the number of moles, 0.01 moles of HAC. And initially we don't have any AC minus, but since we're at the midpoint, we're going to add 50 milliliters of the base, 50 milliliters of the 0.1 molar NaOH equals 0.005 moles of OH minus added. So, since I'm adding since I'm adding a base, I'm going to add to the base. That is 0 plus 0.005 moles equals 0.005 moles. And then 0.010 minus 0.005 moles. We're adding and subtracting the moles, not the molarity. Once I've got the moles, now I'm going to divide by the new total volume. That's 50 milliliters here, plus the 50 milliliters from the beginning is 100 milliliters. So that's 0.1 liters divided by 0.1 liters. So 0.05 divided by 0.1 liters, 0.05 molar. At this point, the reaction comes to equilibrium. That is minus x plus x plus x. And then you can use your Ka expression. And I'm also rewriting this Ka expression every single time because I want to make sure we know what we're plugging into. So that's 1.8 times 10 to the negative fifth is equal to 0.05x over 0.05. This math is even simpler because the 0.05s will cancel out. So this is equal to x. And since x is equal to the H3O plus, the pH becomes even simpler than that. That's the negative log of 1.8 times 10 to the negative 5. That is 4.74. So what's happening in this reaction? Well, all the OH added reacts with half of the HAC to make AC minus. So it's just exactly like the other problem, except that since I'm at the midpoint, I've gotten rid of half of the AC minus, and I've made that same amount, gotten rid of half of the HAC and made that same amount of AC minus, so that the concentration of HAC equals the concentration of AC minus. And just look back at that math. I had 0.010 minus 0.005 equals 0.005, and on the other side I had 0 plus 0.005 equals 0.005. The concentrations were the same on both sides. And since HAC will equal AC minus, then they will always cancel out. And at this point, pH will be equal to pKa at the midpoint of a titration. Not the equivalence point. When you're halfway to the equivalence point, the pH will be equal to the pKa because the HAC will be equal to the AC minus and they're going to cancel out. So how is this calculated? Use the Ka equation. And cancel out AC minus and HAC. This only works at the midpoint, not initially, not at the end point, just at the midpoint. All right, let's just get to the equivalence point. What happens to the pH at the equivalence point? Write your equation again. Always start with your equation. Okay, so since we're at the equivalence point, we are equal where we said we were going to be. That's 100 milliliters of base added. And remember, the base had a concentration of 0.1 molar. So 100 milliliters of 0.1 molar, that's 0.1 times 0.1 is 0.01 moles of OH minus. Now initially we had 0.01 moles of HAC. And initially we had no AC minus, so I'm going to add a base which adds to the base, which makes 0.01 moles over here, and subtracts from the acid, which makes nothing, which means my HAC is gone. I've used it all up. It reacted with all my OH minus. There is no more OH minus in my flask. There's also no more HAC in my flask. The only thing in my flask is a bunch of excess water, and the AC minus is in my flask. So we're going to write a brand new equation. And our brand new equation is going to look like this. AC minus plus the water is going to make HAC plus OH minus. Remember, AC minus on its own is a base. And the number of moles of AC minus is 0.01 moles. And the total volume is the 100 milliliters of base plus my initial, 50 milliliters of acid? That's 150 milliliters. So 0.15 liters. 0.01 moles divided by 0.15 liters is 0.067 molar. And now this reaction is going to come to equilibrium, minus x plus x plus x, and I'll do my K expression is equal to HAC times OH minus over AC minus, and hopefully you are noticing the OH here, which means we are no longer Ka, we are now Kb. I need the Kb of AC minus, not the Ka of HAC. The Kb of AC minus, not the Ka of HAC. So instead of 1.8 times 10 to the negative 5, it's 1 times 10 to the negative 14 divided by that, which is 5.6 times 10 to the negative 10 is equal to x squared over 0.067. So multiply both sides by 0.067, take the square root, we end up with x is equal to 6.1 times 10 to the negative 6. This is a little bit different from before because this is the OH minus. So when I take the negative log of that and I get 5 point something, 5.2, that is my POH, not my pH. So pH is 14 minus that 5.2, which is 8.8. There's my pH at my equivalence point. What's happening in this reaction? Well, all the OH minus reacts with all the HAC to make AC minus in water. So the only thing left in your beaker is AC minus in water. That then reacts to produce, in other words, that makes HAC and OH minus. Okay, so how is this calculated? We need to use the Kb of the conjugate base, not the Ka of the weak acid. Alright, so what happens if you go a little bit past this equivalence point? Let's say you've added 120 milliliters of your NaOH instead of just 100. So first thing is, how many moles is that? 120 milliliters of 0.1 molar. That is 0.012 moles of OH minus added. Also, I'm going to start with a reaction. That should be no surprise. And I'm going to start with what I have. Every single time so far I've started with, I have 0.01 moles of HAC. And now I'm going to add a base. And add a base adds to the base, subtracts from the acid. So I'm going to subtract 0.012 moles. And hopefully your elementary math is telling you that you cannot subtract a larger number from a smaller number. What's left over cannot be negative. I cannot have negative HAC in a beaker. So what's left over is 0.002 moles, but it's not excess HAC that's left over. It's excess OH minus that's left over. The OH minus was in excess, not the HAC was in excess. But what about the AC minus? Well, I only am allowed to produce 0.01 moles of AC minus because my limiting factor is now the HAC, not the OH minus. So my limiting factor is the amount of AC minus that I can produce. Then I will divide both sides by the new total volume, 120 milliliters, plus my original 50 is 170 milliliters. 17 liters divided by 0.17 liters. And that equals, this is 0.012 molar OH minus and 0.059 molar AC minus. But AC minus is a weak base, and OH minus is a strong base. AC minus is a weak base because it will on its own produce some OH minus when it reacts with water, but OH minus is OH minus. So this is now insignificant. It doesn't matter. It's negligible. I don't care about it anymore because now I have a strong base, and the strong base is going to be the thing that does it. So the POH is the negative log of the OH minus, ignoring completely the AC minus because the AC minus will ionize so small that it won't give me a number that means anything. And I end up with 1.9. That's the POH because I have excess OH. So to find the pH, that's 14 minus 1.9, which is 12.1. So what's happening in this reaction? Some of the OH minus reacts with all of the HAC to produce AC minus. The OH minus is left in excess. AC minus will produce insignificant amounts of OH minus in solution. So how is this calculated? You take the negative log of the excess strong base. That is the concentration of the extra strong base because we want the molarity, not just the moles, so divide by the total volume. The contribution from AC minus is negligible. Oh, if I spelled that right, I'm lucky. Very last thing is let's look at how a titration curve would look. Remember we started with an initial pH. We have pH over here. And volume of base added over there. We had initial pH of about 2.7. And it went up a little bit faster than the other one did. And there is still a steep jump. That steep jump is my equivalence point. That was about 8.8. And then it finally ended somewhere around 12. What's important to note is that at the equivalence point, this is above 7, because at the equivalence point what you have left is AC minus, and that itself is a weak base. So the equivalence point does not have to be right at 7 for a weak base, a weak acid and a strong base. Okay, that was our titration. I hope you had fun. See us next time.